Good morning. So within the Hyperfacets project, we're examining a range of hazardous wind phenomena ranging from windstorms that are associated with extratropical cyclones down to mesoscale phenomena such as downbursts and gust fronts. Today I'm going to confine myself to windstorms. We're seeking to diagnose their causes, their dynamics, quantify their intensity, and their climate sensitivity. In this work, we're focusing on the northeastern states defined as in the National Climate Assessment. So our methodology uses 40 years of hourly output from ERA 5, and we're using a purely geophysical definition of windstorms here. So for each grid cell, we identify the hours when the wind speed at 100 meters exceeds the locally determined 99.9th percentile. We're using locally determined extremes to account for the variation in roughness across the domain. As you can see here in the map, the absolute magnitude of the 99th percentile wind speed exhibits notable variability, and if we used an absolute threshold, we would preferentially select storms over the Great Lakes and out over the Atlantic Ocean. So for each event, we're characterizing its spatial extent using the number of grid cells, its intensity using the maximum wind speed and return periods, and also the duration. We're also examining whether each event is a composite extreme using rainfall rate and hydrometeor type, again from ERA 5. We've done quite a bit of evaluation that I won't share with you today relative to in situ and remote sensing observations, plus the NOAA storm database. Each event is equally contextualized within the associated cyclone and the long-term, the 40-year climatology derived using Kevin Hodges' tracker algorithms. So we're using 3-hourly relative vorticity and mean sea level pressure to diagnose cyclones. For the return periods, we're using the Gumbel distribution applied to annual maximum wind speeds. So you can see on the upper right-hand panel the 10 peak events. There was no more than one of these in each calendar year, so I'm going to refer to them by calendar year. In the lower panel, we see the storm coverage, showing that for some of the events, for example, Hurricane Sandy, over 300,000 square kilometers of land grid cells were covered by wind speeds in excess of their locally determined threshold, or if you prefer, 66% of land areas exhibited extreme wind speeds by this metric. The events are shown here, again characterized by the type of cyclone associated with each event, TC being a tropical cyclone, AC Alberta Clippers, CL for Colorado lows, and I've noted the two storms that actually regenerated offshore and formed nor'easters. Also show the inflation adjusted property damage associated with each storm. So these were very consequential storms. In the upper two panels there, I'm just showing you two example events. The 2003 Alberta Clipper, where the blue dots show the geographic centroid of the windstorm, and the red and black dots show the cyclone centroid. I'm also underlying there the NOAA storm damage and death rates. 2018 storm, as you can see, was a Colorado low that took a more southerly track. So there are many, of course, factors that determine how much property damage is associated with each of these storms, but it's worth noting that in fact our metric of intensity, the number of grid cells that exceeded their local 99.9th percentile, when we correlate those with storm damage in dollars, actually has a correlation coefficient of 0.63, which has a p-value of less than 0.05. So there is a strong association between damage and our geophysical intensity metric. What we see on the lower panels here are, this is the intensity of the climatology in each ERA 5 grid cell. So it's relative vorticity on the left, of course this should be times 10 to the minus 5, and on the right it's the pressure perturbation. Overlaying on them is the tracks of each of our 10 largest windstorms, and what we see is the cyclone tracks associated with these windstorms are fairly typical. Their intensity is, however, 10 times the mean of cyclones of equivalent tracks, so they are exceptional in terms of these cyclone intensity metrics. And it's worth noting that the 3 Alberta Clipper storms all passed over periods of relatively low cover over the Great Lakes, but all of them exhibited substantial increases in intensity as they passed over the Great Lakes. So the Great Lakes are acting to greatly intensify these storms. This figure shows the return periods for individual grid cells and shows that each one of these windstorms was associated with some grid cells having winds in excess of their 50-year return period. So these are indeed extremely powerful systems. For each of those windstorms events, we are now conducting WRF simulations to characterize the events in more spatial detail. So we're running simulations at 5 kilometers, 3.3 kilometers, and 1.6 kilometers. We're looking at the skill of those simulations relative to ASOS and remote sensing data for wind speeds, and ASOS and radar for precipitation. We're looking at the value added by going to increased resolution. We're looking at the dynamics. So what are the causes of the embedded maximum wind speeds? Are they dominated by low-level jets associated with the cold front? We're also conducting pseudo-global warming experiments where we're perturbing the lateral boundary conditions in terms of temperature using the mean transient response from CMIP6 models. We're adding humidity as a function of temperature perturbation, and we are also fully de-icing the Great Lakes. The configuration we're using in WRF is as in the new European Wind Atlas, because we know it has high fidelity for wind speeds and some key parameters are there. So just a couple of results from our 3.3 kilometer simulations, where we show in the outer domain here is resolved at 10 kilometers nested within ERA 5, nesting down to 3.3 kilometers over the northeast here. This map shows the topography within each of the domains and also the mean absolute error for the 2018 event relative to ASOS. And you can see there are 3 stations, one of them actually being Binghamton in New York State, where we see substantial mean absolute error during this windstorm event. And these 3 ASOS stations, we've gone back and done some detailed analyses, either experienced local blockage or local very steep terrain that is not fully resolved at 3.3 kilometers. The Taylor diagrams on the right here are for each of our ASOS stations. Now looking at, in the left panels here, the evaluation relative to ASOS for wind speed. So this is done at a 10-minute time step. You can see on average the standard deviation through time here at each station is well reproduced. The correlation is about 0.8, which is at least reasonable. There is more scatter on the Taylor diagrams here for the 2018 event, with some evidence for high normalized standard deviation. But again, it's these 3 sites that I've just identified for you there. The Precipitation characteristics, again, are reasonably represented, but it certainly is poorer model skill, likely because of our selection of the microphysics scheme. Thank you for your attention.